Okay, here's the other two free response to go with section 7.6. The rate at which people enter an amusement park on a given day is modeled by the function e, I guess that's the enter function. Now this is a rate, okay? So they're coming in at this rate. The rate at which people leave the amusement park on the same day is modeled by this function. Both E of t and L of t are measured in people per hour, and time is measured in hours after midnight. These functions are valid for times 9 to 23, so that would be 9 a.m. and 23 would be 11 p.m. At time t equals 9, there are 0 people in the park. And if there were any people in the park, that would be like a plus c when we find the area under this, right? This is like the change, and if we take the integral of this, that's like the change in the number of people. But if we're starting with 0 people, then that's all good, right? It means we're starting from 0. Okay, so how many people have entered the park by 5 p.m., which is t equals 17? So that, we want people, so we're going to do the integral from 9 when the park opens to times 17, and they want to know how many people have entered the park. So this is the expression that gives us that, right? The area under this is a rate. Again, if you want to think about this is people per hour, this is hours. So if we find an area, we multiply the units together and we get people. That's what we want. So let's use our calculator to do that. Let's see, we want to do the area, it's math 9, under the enter function, which is 15,600 divided by x squared minus 24x plus 160, comma x, comma, what are we doing, from 9 to 17, right? 9, comma, 17. 6,004 people. Now, we're talking about people here, so we don't want decimal parts of people. That's just disgusting. So, 6,004 people. Okay. The price of admission to the park is $15 until 5 p.m. So that means all the people that we just found in Part A, they had to pay $15. And after 5, the price of admission is only $11. How many dollars are collected from admissions to the park on the given day? So I think we need to find out how many people came in from time 17 to time 23. Let's do that. So pull up the same thing. We want to do that, but now we want to do it from time 17 to time 23 when the park closes. So another 1,271 people come in. So we have $15 times 6,004 people plus $11 times 1,271 people who came in late, got the cheap ticket. Let's see, 15 times 6,004 plus 11 times 1,271. So $104,041. $104,041. Maybe we're in the wrong business, huh? Did we answer everything there? Round your answer to the nearest whole number. Okay, so we're good. Part C. Let h of t equal the integral from 9 to some t of the, so this is the integral of the number of people who entered minus the number of people who left, 9 to 23. The value of h of 17 to the nearest whole number is 3,725. Find the value of h prime of 17 and explain the meaning of both of these in the context of the amusement park. All right. Now, what does this integral mean? Well, if this were any number, then this part of it here is what we were just doing, right? The integral from 9 to whatever time in the enter function, that's how many people have entered. And then if we did the same thing with this one, that would be how many people have left, right? So if you take the number of people who have entered minus the number of people who have left, you have the number of people in the park, right? So h of 17, which is this, that's the number of people in the park. That means at 5 o'clock, there's 3,725 people in the park. So h of 17, which is equal to 3,725, is the number of people in the park. It's the number of people who have entered minus the number of people who have left. That's the number of people in the park. Now, h prime, let's see, the derivative of the h function, the derivative of an integral, it's just, the integral goes away. It's just e of t minus L of t. And that's the rate at which people are entering minus the rate at which people are leaving. That is the rate. That's like the total rate of change of people in the park, right? Just this one on its own, that's the rate people are entering. This is the rate they're leaving. So when we combine those, we get the actual rate of change of the population of the park. And h prime of 17 would be e of 17 minus L of 17. And we can calculate that quickly here. So let's see, that's 600 divided by 17 squared minus 24 times 17 plus 160. That's e of 17 minus 9890 divided by 17 squared minus 38 times 17 plus 370. And before we hit enter, you think it's going to be positive or negative? Think about that for a second. Let me pause the video. I haven't looked at the answer yet, but I think it's going to be negative because it's 5 o'clock and probably there's more people leaving at 5 than there are people coming in. So let's see. Hey, it is. So it's about negative 380. 380 people per hour. So at that time, the total rate of change, although there are still people coming in, there's more leaving. So the overall rate of change is negative 380 people per hour. Population of the park is going down, just as the sun is going down. All right, part D. At what time t between 9 and 23 does the model predict that the number of people in the park is at a maximum? let's see, a couple different ways you could do that. But here's the easiest, I think. Max people in the park. When do we have a maximum? When the derivative is 0. So that's when the derivative, or the total rate of change of people in the park, is 0, right? It would be increasing, increasing, increasing up to a certain time, and then decreasing after that. So we're looking for when this is equal to 0. So that's when h prime of t is equal to 0. And h prime of t is equal to t minus L of t. Or in other words, when the number of people entering is equal to the number of people leaving. So if you think about it this way, the number of people entering for a very long time during the day is the number of people coming in is bigger than the number of people leaving, right? But at some point, the number of people leaving catches up to the number of people entering. And it's at that point where this catches up to this and they're equal, that the total number and the number of people leaving surpasses this. That's when we get our maximum number of people. Because after that point, more are leaving than are coming in. So let's see if we can set those two equal. And I'm just going to do that by graphing them and finding the intersection. So I'm going to type this stuff in yet one more time. Let's see, what are they? X squared minus 24x. If you get tired of doing this when you're sitting there taking the 3+ hour AP test, just remember that college credit that you're going to get will carry you through. All your hard work will pay off. All right, what kind of window do we want to look at? We're talking about values from 9, the times are from 9 to 23, and we're talking about pretty big y values, right? The number of people in the park at 5 was, what, 3,725, so maybe, and they were decreasing, so let's try 5,000 for a maximum and see if that does it. We'll scale by thousands, whatever. Let's graph them. See what we got here. All right, there we go. That's where they are equal to each other. Second, calculate. Oops, second, try that again. Calculate. Intersect. Looks like they intersect at 15.795. There you go. And sure enough, that was a little bit before 5 o'clock. That's what, 3 o'clock? And what, 3, let's see. You could just do, if you were curious, 60 times 0.795. So about 3:48 in the PM. All right. That one took a good 14 minutes, so it was a long one. Let's see if we can get through this one a little faster. The number of gallons P of T of a pollutant in a lake changes at the rate. So again, we're given a rate, 1 minus 3, blah, 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 gallons per day, where T is measured in days. There are 50 gallons of the pollutant in the lake at time 0. Okay, so we're starting with 50 gallons. That means any integral that we take here is how much it changed from a starting point of 50. Right? Let me say that again. Any integral that we take here is how much it changed from a starting point of 50. Okay? The lake is considered to be safe when it contains 40 gallons or less of pollutant. Well, that's not a very good starting point then, is it? I don't think I want to swim in this lake. And who's to say what's safe for some toxic chemical anyway? Jeez. All right. Is the amount of pollutant increasing at time 9? Well, this is the rate right here. So I think we just want to plug 9 in here, right? Is the amount of pollutant increasing at time 9? We just want to see if this is positive or negative. So let's plug 9 into that. We get 1 minus 3e to the negative 0.2 times the square root of 9, which is 3. So it looks like it's decreasing. It's negative 0.646. So P prime of 9 is equal to negative 0.646. So the amount of pollutant is decreasing because that's negative. Again, you want to find increasing or decreasing, then you're looking at a derivative, and they gave us that derivative. For one value of t, will the number of gallons of pollutant be at its minimum? Justify your answer. Well, let's go ahead and graph our derivative here and see what we're looking at. One minus 3e to the negative 0.2 times the square root of x. And this is gallons per day. T's measured in days. So I'm just trying to think what we should set our window to, how many days we should go out. I don't know, maybe we should go out like 100 days? I don't know. Sometimes they give those values, but they don't really have it here, so let's go out to 100 days. Well, 0 to 100 days. And these are going to be pretty small numbers, so let's just go to our standard window and see how that looks. Our standard for the y's, anyway. All right, that's much closer to that axis, so I think I want to go back and make those smaller. Let's go like negative 2 to 2. Okay, now remember what we just graphed. We graphed this. This is the rate of change of pollutant. So the derivative is negative and then positive, right? So it's decreasing and then increasing. So that is the minimum value right here. So let's find that place where it crosses. I guess going out to 100 days wasn't a terrible choice. So it looks like at 30.174 days, minimum at 30.174 days. Mark your calendars. That's when you want to go for a swim. In 30.174 days. Why is that a minimum? They want us to justify our answer because the p prime of t function goes from decreasing to, actually, it goes from negative to positive is what we want to say, right? Negative to positive. All right. Part C. Is the lake safe when the number of gallons of pollutant is at its minimum? Well, to figure out how much it's changed, we'd have to find the area, right? The change in pollutant is the area under this from 0 to that value. So remember, we're starting from 50. We're starting at 50 gallons, and then plus whatever this is. It's going to be a negative number because it's a negative area, right? From 0 to 30.174 under the p prime of t. So let's see. Second, calculate. Let's find the area from 0 to 30.174. Should shade right up to our spot where we cross there. Come on. Negative 14.87. So that's 50 minus 14.896, which is 30, oh sorry, let's do that. 50 minus 14.896, 35.104 gallons. So it's safe. Put that in quotation marks. You can decide how much pollutant you want to expose yourself and your family to. Less than 40 gallons must be safe, right? An investigator uses the tangent line approximation to P of t at t equals 0 as a model for the amount of pollutant in the lake. At what time t does this model predict that the lake becomes safe? Let's see. How do we find a tangent line? Excuse me for a second. To find a tangent line, we need a point, and at time 0, there are 50 gallons, right? That's our point at the origin, and our slope is plugging 0 into this. We get 1 minus 3e to the 0, and e to the 0 is 1. And you plug it in your calculator, but it's just 1 minus 3, right? Negative 2. So that tangent line is, instead of having, you could write it as y equals, but it's a approximation for pollutant. So the amount of pollutant, y equals approximately, that is a y-intercept, right? So it's like negative 2t plus 50 is the equation for the line. And what time is that going to predict that the lake becomes safe? Well, the lake becomes safe at 40 gallons, right? So setting that equal to 40, we get 2t is equal to 10, or t is equal to 5 at 5 days, right? So that's the answer. Maybe we could just, like, a little bit of reflection on that. Why did this model predicted that the lake became safe at 5 days, but like the real calculus up here predicted that it didn't become safe? Oh, actually, we didn't know when it became safe exactly, did we? But it appeared from the graph that it was certainly later than 5 days, right? After almost a month, it was just a little bit under that. Why did this tangent line predict so much earlier? Well, if you remember what the graph looked like, it was steeper, right? It started to flatten out. The slopes were getting smaller, so this overestimated because the amount of pollutant was not decreasing as fast the whole time. So anyway, we weren't asked about that, but it's worth thinking about. All right.